Hello students, welcome back. Let's continue working on the method of proof. The first topic, proof by algebraic manipulation. Here's a rough classification. We can classify direct proof and indirect proof, and the direct proof roughly by proof by manipulation and proof by implication. And further indirect proofs can be classified into proof by contradiction and proof by induction, which we will talk about later. Here we're going to focus upon proof by manipulation. So how does it work? Here is one of the simplest possible example. Start from the left hand side, work out, and then get to the right hand side. Kind of like this. Almost the simplest possible example for algebraic manipulation. Or sometimes it is more convenient to start from the right hand side and work out, and then you get to the left hand side. Manipulation itself may be a little bit tedious, just as you see here with dots and things like those, but the overall structure remains the same. Start from the right hand side, work out. In the end, you get to the left hand side. By the way, please note that this part left completely empty. This is not a separate sentence, another sentence like that. This is just continuation of one sentence. We'll come back to this issue. All right, so far so good, but there are some harder types of proofs. Look at this example. If you start from the left-hand side, do you think it's easy to manipulate the square roots here? Oh, that looks really challenging. Now, what if I start from the right-hand side? Right-hand side is too simple that you have to make it more complicated in very strange direction to get to the left-hand side. That's not really natural. It's not likely to work very well. Obviously, we need some work. And that's when we need appropriate setup. What do you mean by setup? Well, we can manipulate not just a part of something we want, but the entire statement. Rework the entire problem and rewrite it in a little bit different format, which is actually equivalent. Okay, look at this problem and a new problem. As a matter of fact, these two problems are equivalent. Why? This one squared versus that one squared. If both are positive, then of course they're equivalent. What if this is negative here? Then this is always true. Left-hand side is always positive. So yeah, they are equivalent. So sometimes it is easier to reduce the original problem into equivalent but simpler problem. That's what I'm talking about here as a step one, setup. So that can get a little bit tricky, but with some repeated exercises, you're going to get used to it. Shall we begin? Okay, let's begin. Here's the setup. By taking square of both sides, we can simplify the given problem like this. Remove the square root by square rooting, and then right hand side we have to square it. Now, is it possible to start from the left hand side and work out and go to the right hand side, or vice versa? As a matter of fact, that's still a little bit hard. It's not impossible, but still a little bit hard. So let me tell you another very typical technique. Subtract one from the other and then try to prove this thing is greater than or equal to 0. Okay, will this help? Well, okay, let's try. This may. So let's copy and paste this thing. All right. And then let's begin working out. a squared times c squared first, and then outside a squared times d squared. Inside b squared times c squared, and finally last b squared times d squared. How about the right hand side, the second term? A squared c squared, first term squared, and then 2acbd, and then b squared d squared using the complete square formula. Okay, let's align the equalities. And by the way, let's rewrite like this. This is blue. And then this one is the red term. And that'll help you understand this manipulation. Please bear with me. Okay, all right. So we want to prove this. And then instead, let's try to prove L minus R, left minus right, is greater than or equal to 0. And left is blue, right is red, and let's write it like this. And then let's further manipulate. A squared cancel each other out. And then b squared, d squared cancel each other out. And what do you get? A squared, d squared plus, no, b squared, c squared minus 2abcd. And this one came from the blue terms. And that one came from the blue terms again. And then this one came from the red terms. Okay, let's look at everything. Does it make sense? So left minus right, and then just applied algebraic manipulation and further algebraic manipulation. And go ahead with further algebraic manipulation. Please recall that this is first term squared, second term squared, times twice of first and second. So this is complete square. AD minus BC, total quantity squared. And this is squared, so always that's greater than or equal to 0. And wasn't that what we wanted to prove all along? What do you think? Here is a correct proof. And if you want to see proof, actually this is already in there. But if I just open up the answer key and explain, you never learn. So I just took step by step. If you really want to learn, then you should do these on your own. You'll have plenty of chance to do that. If A is B greater than or equal to 0, then prove this. As a matter of fact, we have two inequalities. Arithmetic mean is greater than or equal to geometric means, and then geometric mean is greater than or equal to harmonic means. You have to prove two inequalities. So this is two proof problems combined into one. You can use similar kind of technique. You have to do a bit of setup because we have square root. It's going to be a little bit difficult to manipulate this one. Similar thing about absolute values. It's going to be a little bit difficult to manipulate the absolute values. So by taking square, you can kill off at least some of them. Good luck about that. Okay, all right. Now, do I have enough time for the last example here? Discussion on incorrect proof. Okay, let's talk about it. Here's an attempted proof of this blue term is greater than or equal to this red term, which we already did. And wrong proof. This is blue. And this is red. Blue minus red is greater than or equal to 0. Let's see. Is that just manipulated from here? Looks okay to me. Apply algebraic manipulation. Blue became that. Red became that. Anything wrong here? Again, looks okay. A squared, c squared cancel each other out. B squared, d squared cancel each other out. So what's left will be a squared, d squared from blue terms. And b squared, c squared from blue terms. And from the red terms, we get 2acbd. And the multiplication is commutative, so you can write it as abcd. But in any case, we got that. Oh, excuse me. This should be blue. All right, and then this can be manipulated further into complete square form. So far, so good. And complete square is always greater than or equal to 0. So looks like we have everything perfect. But this notebook says this is a wrong proof. What's wrong with this proof? Think about it. While you're thinking, let me go get the correct proof. Yep. Correct proof from here. Okay, all right, here we go. Okay. Wrong proof here and correct proof here. What's the difference? Anything wrong from the first line? Blue minus red. They look exactly the same. How about the second line? Blue minus red, just a bit of an algebraic manipulation to blue and red respectively. Exactly the same. And some cancellation. This and that. Again, this part, that part, exactly the same. And then, okay, I may have skipped a step here, but I could have easily inserted one. So this is AD squared minus 2AD BC plus BC squared. Yes, I can easily insert this one. Exactly the same as before. And then exactly the same conclusion as before, but this is wrong and this is correct. What's the difference? Well, I just asked you an enormously difficult question. If you can answer that, then as a matter of fact, you wouldn't be listening to this lesson at all, as a matter of fact. So I'd better give you the answer here. The difference? This is the continuation of just one identity. So left minus r is equal to that, which is equal to this. That's equal to that, and that's equal to this, and that's equal to that, and finally that's greater than or equal to 0. And this is just continuation of one big inequality. Equal, 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 in the end inequality. So overall this is inequality. This is just one inequality. So if you had really white paper, you could have written everything in a single line horizontally. Of course, that's really hard to read, even harder to write. So we use this kind of mathematical grammar. Write all these vertically and then align all these inequalities and so on. And another thing, please take a look at this point where I'm running my mouse around. This point is completely empty. That means this inequality or this each equality corresponds to the previous line. So that third line is equal to fourth line, and that's equals to fifth line, and so on and so forth. So this is a continuation of just one big inequality, starting from left to right, and then algebraically manipulate, work out, work out, work out, work out. In the end, we got what we want, greater than or equal to 0. So this is correct proof. Now let's go to the wrong proof here. We have a complete inequality here, and then a separate inequality. These two are different inequalities. And another sentence, and another sentence. And how are they related to each other? Not explained. So this is a little bit wrong way of writing. All the algebraic manipulations are correct, but in terms of mathematical writing, this is wrong way to write. Mathematics is kind of like language, and it was created, really seriously, it was created for communication purpose. If you use wrong grammar, then you won't be able to communicate properly, and then there will be miscommunication, and that will cause a heck of a lot of damage. Sometimes people die from that if the application is related to some heavy machinery or some construction and things like that. And that's, as a matter of fact, rather commonplace, to tell the truth. Tragically it may be, but yes, it is. So it is utmost important to communicate perfectly. And that is what we really, really, really emphasize, 3,000 and up. Up to 2,000, most of our effort was about solving mathematical problems. 3,000 and up, it's about communication. And this is not a good communication. This one is. Okay, here's some explanation of key issue. I wrote it like this, but I don't know whether you can really understand what kind of thing with just this. So just go through these lessons. That probably is better. And by the way, it is possible to correct this proof or this wrong proof where we have all the separate sentences into some form like this, and then turn it into proof by logical implication. So this effort here is a failed effort to prove using proof by algebraic manipulation. But by inserting some logical symbols and expressions, you can turn this one into correct proof of logical implication. But what can I say? That's much harder proof. So if you can do this, then you probably won't be making this kind of mistake. So hey, what's the point? But in any case, yeah, here's a corrected proof anyway. Okay, that's where I'm gonna stop. And please try not to make these kind of failed mistake. And yeah, I will scrutinize these kind of things. Heck, even in Math 1600, I used to take a couple of points for these kind of problems. So in 3000, if you make these kind of mistakes, you'll have to expect something like 50% off, not just 10% off or 5% off.